Okay, so today's talk is essentially will be based on a special phase or a particular phase of the early universe that is called reheating. So in this talk, I'll be talking about some specific results that we have obtained in this particular phase. And we have been working on this particular topic for quite some time. These are the collaborators that a few of my students are also here. Okay, so how does the present state of the universe arises? So this is the present state in the sense that I'm particularly talking about our campus. Just to show you that by looking at this picture, you may like it. If you want to visit this our campus, you can certainly come and you can write to us. All the informations are available in our website. So. So please do visit us because it is actually the northeast part of India where quite less number of people usually come. So I invite you to visit our campus. And by the way, so here I hope many of you have heard this. This is where the Kamakha temple is there. So it is just opposite to the Brahmaputra river. Okay, so how does the present state of our universe arise? So in order to, so this is the basic question that people, whoever has, if you have some bit of knowledge about the universe, or if you want to understand more, this is the first question that you can ask, that how the present state of the universe. So in order to understand that, basically the present conclusion of the present state is based on mostly observations. Okay, and our current observation says. Current observation says that if we go backward in time, starting from the present state, universe will go from cosmological constant domination to matter domination, radiation, and then the inflation. After that, we don't know, but at least up to this, we know quite very well how the universe has gone through various successive phases from inflation to the present state. But my present talk will be based on a particular phase that happens between this inflation and radiation, which is this reheating. And why this reheating is important, given the state that inflation has happened and then radiation, matter, cosmological constant successively emerges. This reheating is very important and it has to happen. And let me just try to motivate you why this should happen. Okay, so inflation is essentially a phase of the early universe, which you require in order to explain some cosmological observations that many of you know. So it is essentially a phase where the universe has undergone exponential expansion, and moment you assume that particular phase happened, this inflation happened, then immediately you realize that because of this exponential expansion, you will land up getting a very supercooled universe where nothing is there. Except a constant background energy density, which we typically call inflaton. Okay, so that means inflation gives you essentially a supercool phase with a constant background energy density with some fluctuations on top of it. But we know that our universe should be hot at some point. So that means in order to get from this supercool to present phase, this hot phase, you need to have a transfer of energy by some mechanism, and that's simply called reheating, essentially. So, so inflation has to end at some point, otherwise we will not exist, because we want to have our present state. So inflation has to happen, and it has to end at some point. After the end of this inflation, you expect that this inflated energy, whatever the energy that was there in the background in the form of inflaton, has to be transferred to the matter field or the visible field, all the fields that we see today, by some mechanism, and that is precisely is essentially the reheating phase. Whether this reheating phase will be prolonged or how efficient the reheating phase will be, depending on what is the model that we're talking about. So conventionally, what people do, that because it has happened very early, okay, so and you don't have, and you can clearly understand this is a beyond standard model, because we know inflaton is definitely out of the standard model stuff. So conventionally, what people do, we need to understand first how to successfully get the reheat. So that is the first thing. Before we talk about any observational aspects, any observational consequences, first thing that we have to successfully do the transfer of energy from infrared onto visible field, matter field. So typically what you do, there are various mechanisms, not mechanism, I would say, moment you introduce some kind of transfer by using some field theory interaction, then immediately we'll end up getting various processes like non-perturbative processes, perturbative processes. Those are the processes by which infrared energy can be transferred into the radiation field in general. But one of the points that I should emphasize that because this is happened at very early age before standard hot Big Bang, so direct observable is of course very difficult because observation is extremely difficult. What happened at that time if you want to directly observe. And then another point is because it's highly non-equilibrium process, infraton is going to be decaying constantly. This time evolving process, and that there will be after that, because finally we want to have a thermalized universe. So that means this non-equilibrium process will have there will be a thermalization. Yesterday there was a talk on this, and the thermalization process will typically naturally would expect that there will erase all the microphysical processes, that fundamental physical processes that are happening during this period. So naturally it will erase many information about what has happened during this period. And of course, because this is the beyond standard model stuff, you will need to know the appropriate theory by which you can do this transfer. So it's difficult. It's basically difficult in some sense. In terms of observation, it's very difficult. So since I'm talking about observations, let us try to ask these questions. Given the inflationary model, what are the things that should we expect to observe? So that is very important. But what are the observable that we expect if I have inflation? If you have inflation, that naturally you expect that there will be homogeneous, because we know because in order to explain the homogeneity of the universe, we have invoked this inflation. So that means you have this background which is a homogeneous background, and then naturally you would expect, moment you have homogeneous background, you would expect there will be fluctuations. Okay, so these are the two things that in a broad sense you would expect. And then apart from background, these fluctuations can be of different type. Scalar type, and you know how those scalar type fluctuations can be observed in various contexts, in the CMB and fermion, and also scalar type in the dark matter, and the vector type where you can see in the large scale magnetic field also there is fluctuations, and then tensor type, various tensor type fluctuations that you should expect to observe. These are the things that you should observe. So what this reheating does, reheating essentially gives, because reheating is the transfer mechanism of energy from infraton to all the visible fields. So that means it appropriately transfers its energy into the various fields that we see today. That means it is very crucial that we understand this reheating, because that is where, so how this reheating transfers its energy to get this particular state of the universe and all these fluctuations. That means in the background and in the fluctuation, there must be some information somewhere hidden of the reheating, because that has to be there, because reheating is essentially telling you how this energy is transferring into the state. Okay, so let me just, in this slide, I'm just telling you where we stand at the present, in the present context from the Planck, if you are talking about the CMB. So this is in the NSR plane. We all know this NS is essentially the spectrum corresponding to scalar fluctuations, and this R corresponding to tensor fluctuations. So because here at this level, here in this plot at the level of fluctuations we are talking about. Of course, background is there already. So in the NS and R plane, where you stand. So particularly, I'll be focusing on this one special model, which is alpha attractor, which has recently got very popular. And mainly one of the main reasons that alpha attractor got popular is because all the power law model, simple power law model that we know for inflation was basically ruled out because of high tensor to scalar ratio. So that's why this becomes very popular, because it has some supergravity, some interesting way to construct this kind of model. Okay, so now I hope you, I have convinced you that reheating has happened. So that is the fact. Of course, if you assume inflation, reheating has to happen. energy transferred to visual matter field. And such information must be imprinted somehow into the background and fluctuations, because inflation has transfers energy to background and fluctuations. Then the question is where and how such informations are imprinted, and how do you proceed to identify? So that is important. And this will certainly help us understand the beyond standard model physics as well, because influence is the beyond standard model stuff. So that means we already in the reheating physics, beyond standard model is already there inbuilt. And then there are a lot of other puzzles that you all know in the context of cosmology, which may give you some hint how to solve this problem if you understand how this transformation happens. Okay, so the plan is first I'll talk about reheating phenomenology. In the sense, first I'll talk about the difficult part. We want to try to understand the basic phenomenological part of reheating, how to construct the reheating, and then how to understand and in which parameter space reheating happens. First thing that I'll talk about, that identifying the parameter space within which this reheating can happen. And then we try to understand, looking at the parameter space. Sorry, there's just spelling mistake. So looking at the parameter space, I first talk about special reheating model, which is called universal reheating, and I will talk about this. What is the meaning of this universal reheating? And then its prediction and constant. Then gradually, step by step, I'll try to incorporate coupling and then see what are the predictions. So basically, I'll first talk about universal, because universal means it has to happen. It will happen. That is why it's called universal. And then once you understand that universal, then we gradually systematically introduce couplings and then try to see what are the predictions and how could we possibly see in a future experiment. And then finally, okay, so phenomenology. It is simple because it's a beyond standard model field, inflaton. What you do, you just introduce some kind of coupling with either Higgs, or you introduce some other scalar, or whatever fermions, standard model fermions that you have. Simple. You add this kind of coupling, and then with this coupling, you try to understand how your inflaton energy is getting transferred into the fields, and finally you reheat the universe such that you create the appropriate state of the hot Big Bang, and which can be perturbative and non-perturbative. My current talk will be mostly based on perturbative. I will not talk about non-perturbative because it unnecessarily complicates the thing. This is the model dependent part, because it depends on what kind of coupling parameter you are introducing, what kind of operators you are introducing to transfer the energy. Another part, which actually it has been realized just, I think, just last year. I think realized in the sense that there is a gravitational decay of this inflaton. How does it happen? Because you always have this kind of coupling in the theory, minimal theory. You have this inflaton coupled with the energy momentum. You always have this, because if your matter is minimally coupled with gravity, you always have this stuff. Okay, so that means your inflaton can transfer its energy through graviton by this 3-point interaction naturally, because it is there. You don't have to introduce anything else. And the most important point is you don't need to introduce any new parameters. Just this parameter, this 1/mp, because that is naturally there in there. So that is why I'm saying it's universal, because whatever you do, this transfer, this particular process will be there all the time. Okay. But everybody, it was known, but it was never asked this question whether this particular channel of transferring energy from inflaton will really reheat the universe or not, because naturally you would expect, because this is 1/m Planck suppressed operator, so you would expect that this is very low. It should be, decay rate should be extremely low, so that maybe universe will never be reheated simply because of the 1/m Planck mass separation. Actually, recently we have asked this question in this paper, that is it possible to reheat this universe simply by this gravitational interaction? And answer is yes, that is possible. Of course, there are some constants that I'll talk about this. So answer is, so this is very recent understanding that this part will always be there. Whatever model you construct, this part will always contribute to your reheating dynamics. Okay, so in order to proceed, I have to take one particular class of inflationary model. That's what I already mentioned, which is my alpha attractor. So this is basically a 3-parameter family of potential. So basically, you have 3 parameters to describe the potential. And if you look at the form of the potential, you see that at the high value of inflaton field, all the potential will behave like exactly the same. That means the prediction of NSR in the NSR plane, all this model predicts the same value of NSR if you take a particular value of alpha. So that means if you are only talking about at the level of inflaton observer NSR plane, then you cannot distinguish, given alpha, you cannot distinguish which model is giving you the inflation. The infinite number of possibilities. That means simply looking at NSR observable, which are basically large scale observable, cannot distinguish which inflation has happened, which inflation model you should choose. That means there is a large degeneracy of inflation models which can predict. But now if you look at the near the minimum of the potential, various n values will start to deviate. And here reheating plays the crucial role to distinguish different inflation models. Even though they are large scale prediction of the same, but moment to talk about reheating, they can start to distinguish different inflation models. So in that sense, it is a distinguisher. Even though you have this inflation large number of models, but somehow reheating can help you understand to distinguish different inflation models. So that is one of the important applications you can say in terms of distinguishing different inflation models. And what is the distinguisher? We say a parameter. Typically, we call it, which is depending on essentially how inflation oscillates at the end of the potential. And that these oscillations will be, this oscillation essentially, if you average it, it will give you some kind of average equation of state. That is what we define as omega, and it depends on this n. Okay, so this is the setup. Now, once inflation ends, the inflaton start to oscillate, and then during these oscillations, and inflaton now gradually transfer its energy to the inflaton the visible fields. And this is, I think you don't worry about these equations, but I'm just telling you this particular cartoon picture. So this is just inverse Hubble plot. So where this particular line tells you that inflation is happening. And then here, this particular phase is essentially, I identify as a reheating phase, where you can see that evolution of this reheating phase depends on what is the value of n. So that means depending on the value of n, your reheating phase evolution will be different. One inverse Hubble will be different. So this is where it distinguishes the different inflation model. And then Hubble, inverse Hubble will go like this. And then any scale that is exiting at the horizon, it will enter at the present time, depending on what and when it will enter, depending on what kind of reheating model you are talking about. You can clearly see that it distinguishes. 3 lines depending on what is the value of n I have chosen, inflation model. Yes, n means this n. Yes, yes. But at the level of inflation, they are all are same. But moment you start to incorporate this reheating, then you start they evolve different. So that is how you can distinguish. And you have this set of Boltzmann equations, which you perturbatively I can write. If once you know a particular decay channel, you can of course write a decay width, decay rate, and then you can identify your Boltzmann equation. So that is well-known stuff. And then these are the appropriate boundary conditions and constants that I have to impose to solve this problem. Yes.
So it depends on n, because when it's oscillating, its potential is effectively pi to the sum.
Yes, exactly. So basically, when it oscillates near the minimum, I approximate that potential to be of the order of 5 to the power n, and then identify effective equation of state parameter during this oscillation, and that n, that different n will give you different evolution. So that is what the point. Yes.
So this treatment of the inflaton as classical and fluctuations as quantum.
Yes.
Does that continue to be valid during this era where it's oscillating?
Yes. So basically, the oscillation is a background homogeneous inflaton field is oscillating. Yes.
Is it valid to do that separation in the reheating era?
Yes, I think I don't think there is any problem. So basically, what will happen if you are talking about non-perturbative phenomena, then your quantum production will be resonantly produced, and then quantum production, once it is resonantly produced, and then you can treat them as a classical. So the lattices, people usually do that. So you produce resonant production will happen, and then once it is a large number of production happen, then you treat them classical, and then evolve. So I think a classical treatment at this level is I think it works and it's fine.
I mean, there's no back reaction in the potential.
Yes, of course, it is back reaction, because yes, of course, because moment this production will happen, then it will back react in the dynamics. So basically, yeah, of course, it will back react.
Okay, so once there's sufficient amount of
Yes,
production,
then back reaction will happen. Then that is why in the context when you talk about non-perturbative production, at some point non-perturbative production will stop, and then gradually it will evolve according to the perturbation. Perturbation, back reaction is very important. Okay, so so in the in this particular context, I'll be specifically talking about this solving this equation, and then we'll be talking about a bit of dark matter, how this dark matter, how this reheating can shed light on the dark matter parameter space. And then there are two important constants that is coming from the observation. One is the BBN, that your reheating temperature. That means where it ends, at that point you can define a temperature, which is called reheating temperature. And the reheating temperature has to have a lower limit, which is typically TBBN, because we expect that BBN has this prediction, it should not hamper. And then there is a maximum value of inflated energy density that is coming from your non-observation of R, tensor to scalar ratio. Okay, so here what I've done, first we take all these coupling parameters and identify in which parameter region inflation happens. The reheating happens. That is the first thing that we have done. Without talking about detailed analysis, we have taken this part is always there. That is what I said. This is the universal part, and then you take various forms of the coupling, and then you figure out in which parameter region your reheating will happen. So that is the first thing that we have done. So if you take this kind of coupling, and this is the parameter space where reheating will happen. If you take this coupling, there is the parameter space for this coupling. So there is a large number of large region where actually reheating is because the temperature turns out to be less than TBBN. So that is why this parameter is not allowed. So in this way, we have identified the full parameter region where reheating will happen. The predictions will come later. I'm talking about in which region of the parameter space in the coupling and the inflaton parameter, the inflation, your reheating happen. I want to look at this particular region, which is this green region. This green region says, even though these couplings are not there, this is sufficient. This parameter, this universal coupling is sufficient to read that. So that is what we found. Yes. Which one? This one. This one, yes. Okay. Yes.
You are holding one phi as a wave.
Yeah, so basically it is like a wave decaying into
there are two phis, and you are saying it is a decay of a phi.
Okay, decay in the sense I'm saying this two phi decays into I think typically you can have scattering typically.
Or you have one phi as a wave.
Yes.
Then the other phi is your
another just simple particle excitation.
Since you have a potential in which a phi is rolling.
Yes.
So one of the legs could
be no. Here I'm talking about two wave whose momentum is zero momentum mode will produce through this interaction will give you this standard model particle.
So this is a sort of annihilation.
Yes, you can say annihilation. Yes.
Okay. Because I was then coming to this Vikram's question that if you have one phi as a wave,
yes,
and the other is, that means you're treating it as a decay of phi in the presence of a wave, then that wave is an oscillating wave, and if it has a large oscillation.
That process will be subdominant initially because there is no phi. You are talking about there has to be sufficient excitation of phi. Because your dominant energy component
in the potential, phi has a value. Okay, maybe we'll discuss it
later. Yes.
Want your minimum reheat temperature to be 1 TV or
No, TBBN. So there is a TBBN.
TBBN, right?
Yes,
Yeah.
TBBN. Yes. It is like 10 MeV.
Yeah.
Okay, so as I told you, first because I identified the region where my universal reheating can happen. So let me just first focus on this because it's universal. There is no parameter to control. Whatever it predicts, it predicts. So that is the best part of this particular scenario. So in this region, if I'm focusing on this region, so all this coupling will be either negligible. You can set it to be 0 for the practical purpose. You can compute everything just assuming that there is no such coupling. And this is the only process that will give you the reheating. So we don't have this, and then another parameter which is there. If I want to talk about dark matter, because dark matter does not play in the reheating process, because the energy density component of this dark matter will be extremely low. So that is why it doesn't hamper. If you introduce the dark matter, it doesn't really matter for your reheating process. That's why this parameter is just the parameter which, when you talk about dark matter, it will come. Otherwise, the full reheating process will be controlled by these two parameters, which is completely inflatable. There is no reheating parameter in the system. Okay, so now I have already told you that reheating happens, because that is what we parameter region show. Reheating happens. So now, moment I assume that reheating happens, or if that is what we have shown, now we can ask where we are in the NSR. Then if I assume that this particular reheating process is the dominant. So then we see, since there is no parameter, what happens is that this omega phi, what was this n, actually gives you the reheating temperature, because there is no other parameter to tell you which one is the temperature. That is why what happens is that whatever be the, so for a particular value of n, it will give you a fixed temperature. So that means if you fix your inflaton potential, it automatically fixes the reheating temperature. What would be the reheating temperature? Omega phi, okay, omega phi is related to n, which is n minus 1 by, that is what, yeah, I should have written n rather than omega phi. So this one.
Effective
equation of state. Yes, yes. So basically what it turns out that if you take any particular value of n, it automatically fixes your reheating temperature. That is, I mean, it is interesting that you don't require anything. You fix the model, your reheating temperature also fixed. That means everything is fixed to the present universe. You don't need to do anything. And since the read, yes.
Just go back to this Raghavan coupling. So you assume minimal coupling.
This one.
And
Yes, just minimal setup, minimal. Just your Lagrangian and minimal cup. Yes, nothing else.
Yeah, but the thing that gauge invariant is this R, right? The perturbation is R, which is graviton mode.
Yes.
But that can also have M-plan suppressed coupling. The inflaton will also naturally have M-plan suppressed coupling directly to matter.
Yes, that is what I think. This is the matter.
Different, right?
No, the same thing.
No, this is the graviton coupling, which is minimal. And it's exactly 1 by M-plan.
Yes.
But there will be 1 by M-plan with some non-trivial coefficient that comes from quantum gravity. Couplings of the direct coupling of the inflaton to matter fields.
Direct coupling, because you are saying, is it because of some quantum gravity effect? So then there will be some free parameter. Yeah, so that quantum gravity, that means you have to talk about some gravity, quantum gravity model.
But in general,
It can have.
be a similar size.
Yeah, so those will be like, yeah, you are right. So those will be like high dimensional operator 1 over M Planck plus some coefficients. That is what you are saying. Yeah, so here I'm just saying just simply this one, nothing else. Matter. This one, nothing else. Yeah, ALM, yeah, that is what I'm saying. Then you have to introduce some model. I'm saying, even though that is what this couplings are there, these are the matter couplings. I'm saying if this matter couplings is negligible, or let's say by some symmetry, just these are not allowed, then this is sufficient to reheat the universe. That is the point that I want to make. Okay, so and since this omega phi, a specific value of omega phi will give you a specific value of reheating temperature. So that's the prediction. And then moment you solve this, you will find that this is where the previous analysis has shown they did not talk about too much on reheating. So they are saying that there is a large parameter region where your this alpha attractor model lies. So, but moment you talk about reheating, you cannot have this. You have this very limited region of parameter space. So that means, that is what I'm saying. Reheating can tell you which inflator model to choose, which was this was like a new thing, because we never talked about that the phenomena after the inflation can give you constant on the inflation. But here, reheating itself is giving you some kind of constant which inflator model you have to choose to get the current state. And it predicts a specific value of NS that you can clearly see from this plot. And also it tells you that that this reheating phenomena will happen, it will be successful only when your omega phi is within this region. Okay, so that is what the constant that is putting, that your omega phi or n should be within a very specific value of value such that your reheating will happen. Okay, so now that is related to, what is this? This is related to large wavelength fluctuations, scalar fluctuation, tensor fluctuation. Now, if I talk about dark matter, let's say, because reheating, once reheating has happened, then dark matter you can introduce, and you can see what kind of dark matter parameter. Yes.
Need to fix the complete model to fix n, because n in reheating phase we can just assume that V is simply proportional to phi to the power n.
Yes.
Right. So suppose we have a model which is some Starobinsky model, but at the end, if you just modify the model such that we get this potential is phi to the power n, right? So that also works, right?
Yeah. So I think you are talking about Starobinsky. Starobinsky is already there in this.
But I'm saying some other model also, but we don't need to model the complete inflationary period, right? To constrain the n.
No. What I'm trying to say, that once you are, I'm giving you a inflation model, that automatically tells you, if I don't need to introduce anything else, that if your inflation ends, then there will be reheating. If the reheating happens solely because of the gravitational decay, then you can get the present in without introducing any new physics in the model. That is what I'm trying to say through this particular analysis.
That I understand.
Yes.
Maybe we can discuss.
I think your restrictions are coming because you are assuming a alpha attractor potential, which is very flat.
Yes.
So you have a very small R to begin with, just like the Starobinsky model. Yes. So you cannot compare this journalist diagram with yours, because here it's a general, all kinds of potentials are taken.
But here?
Yeah.
No, this is alpha attractor. No, this is alpha. This particular, this is for alpha. Yeah, I think you cannot.
I cannot read the left hand side. What is the range you're taking for R?
This one?
Yeah.
No, this is R002. This is within, this is just Planck. This plot is for Planck, given by Planck.
Yeah, but this is for all kinds of models, right? This is not for alpha attractor.
This particular model?
Yeah.
No. They have specifically this plotted for alpha attractors here. For different alpha, and you take your different n value, and then these are the region where this alpha attractor. So here, these lines are various alpha. Actually, it's not visible probably.
Okay, we will discuss later.
Yeah, I mean, this is specifically for alpha. You are talking about probably the first plot that you no, that was for different model they have been, but here this is for alpha. This particular region. Okay, so now. Okay, so now we can, because now have successful reheating because of this, then we can easily talk about dark matter. And since there is no parameter except the dark matter mass, you will see that your dark matter mass should be, like if you are talking about scalar type dark matter, sorry, this is the fermion type dark matter, then dark matter mass should be within this very narrow range. You cannot have any arbitrary value of dark matter. This should be very within valueness so that it can satisfy the Dirichlet density. Similarly, for scalar, it would be within this range. That is it just predicts that if you are given, if I'm giving you inflaton specific inflaton potential, this should be your mass range, the dark matter. Of course, as I told you, everything is universal, means there is no interaction I'm introducing. Okay, but now the problem arises when you talk about gravitational wave, small scale gravitational wave. So we know that inflation actually enhances all the quantum fluctuations that is there, and then it will pass through various phases. This is because this is weakly coupled, without getting disturbed, it will pass through all the phases, and this various fluctuation will see these various phases. And moment you take into account this gravitational wave passing through various phases, what you observe is that they have a very precise prediction of spectrum or gravitational wave spectrum, specifically in the large frequency range, high frequency range, because those high frequency range we essentially see those this particular phase. Okay, and since my inflation model is constrained by within a very specific region of equation of state, the spectrum is very precise. I mean, meaning that if you say that my universe is gravitationally reheated, then your power spectrum of the gravitational is very precise. I mean, it is just predicted that particular T. And moment you incorporate this, what will happen that there is a constant coming from the BBN, because as I told you, BBN is a place where many physics we have already seen. So what happens is that this energy cannot grow because these gravitational fluctuations will behave like a massless particle. It's a relativistic particle. So that means you cannot grow whatever you want. So what is happening that at some point there's a BBL line, that means gravitational wave energy density should be less than some amount of energy such that it does not hamper the BBL. So that constant you have to satisfy. The moment you satisfy that constant, you find finally that this gravitational reheating is actually a very highly constant parameter space in the inflation space, where that it rule out almost all the alpha values. Only alpha value that exists is 1, and then omega phi, this omega phi is 1. This is, so if I assume that only universe is reheated gravitationally, this is the only one that is survives. At least our present analysis predicts this. Okay, so now, since it's giving you highly constrained system, that is, we have understood that in the if a universe is reheated by gravitational interaction, then very specific inflationary model is only allowed. So that is what we have found. Now let us try to relax that. What I do now, let us talk about this EOLO region. What is EOLO region? EOLO region is where we have now introduced coupling, and then see what are the effects. That means now I have this universal this term. Already it is always there. Remember, this you cannot avoid. This is always there. And then there is another. I am specifically talking about specific channel for reheating, which is the fermionic channel, means inflaton decaying into fermions. So you can have your own possible channels because for the reheating. I have taken a specific channel through which inflaton now can decay, and then you can redo the whole analysis. And now, since you have now extra new parameter H, that will fix your TRE now. Now you have new parameter which can control your TRE. During the for gravitational reheating it was fixed, but now it is no longer fixed. Now you have a new parameter which can control your TRE. So then, depending on various omega phi, you can have parameter space within this NS and R. So that is what we have seen. So because now you have the freedom, so now it is not restricted no more. So you can have for different value of omega this omega. Then you can talk about your where your inflation model lies within this NSR. Okay, so now you can again incorporate, because your omega phi can be large. So again, you can incorporate this BBN constant. If you further incorporate the BBN constant, then what we found that in alpha, this is the inflation parameter, and TRE, only this region is allowed. Okay, so and here, if you look at this, here I have written TREGW, which is essentially the temperature for which this hits the BBN. So that is why these new constants come, because of this small scale tensor fluctuations. Okay, now do I have time? No more time. Okay, 1 minute. Okay, now let me just talk about dark matter. So now I have introduced fermionic decay of the inflaton into fermion. Now we can talk about again dark matter. Remember, dark matter does not hamper your reheating process. Whatever conclusion that I made before is intact. Now only thing that I can talk about how dark matter can be produced through this. So we can have various mechanisms, something called WIMP and FIMP. Let me not go into detail. So let me just tell you the final result, which is very important. So typically, when you talk about WIMP, that is weakly interactive magnetic particle, this is a special kind of mechanism which dark matter physicists do produce dark matter, where your dark matter is always in thermal bath, and at some point, because of the coupling strength, it will decouple from the thermal bath. So that is typically WIMP. And simple WIMP scenario typically predicts that your cross section with the thermal bath should be of the order 10 to the minus 3. And it is almost pretty much a large parameter space of this WIMP is ruled out from various experiments. I have shown these various experiments where so this line is essentially your WIMP line. But the moment I introduce reheating, what happens? A new parameter space opens up. That is, I think this discovered actually this is the second paper, and there is a first paper that one month back came up. So we were doing parallelly. So we found that moment you introduce reheating, that immediately opens up a new parameter space for the WIMP, where you can look for. And these are the parameter space. So this is usual WIMP line where the cross section is around 10 to the minus 9. And then forget about this below point. So this point, above this point, these are all WIMP line where your mass versus cross section lies. And these are all WIMP like dark matter. That means there is a huge parameter region exists where this WIMP like scenario is still valid, and which has not been explored by the experiments. So there are future experiments that are coming up like CTA, who are essentially trying to detect, trying to understand this parameter region. So let me not go into detail. I mean, I can. Yes. WIMP.
What is this cross section?
Yeah, this is annihilation cross. Yes. I mean, if you talk about just simple WIMP, and then if you your cross section should be have a total cross section basically. Yeah. Should be of the order 21 so that you get the correct rating. So that is the standard. Yeah, no, freeze out. Everything is freeze. But only thing is usual analysis of WIMP typically they do in reheat during the radiation domination. But moment you introduce your reheating phase, then the reheating phase, your dominating component is not radiation, it is inflator. So that is why the process becomes completely different. No, it already freeze out. It was freezing out. Yes, too low. If cross section is too low, and yes, that is.
So the freeze out is during reheating.
Yes, exactly. When it happens during the heating, then your new parameter space appears because of this particular. Okay, I think I don't have much time. Let me not read it out. This is the conclusions and future direction, and can think of. Okay, thanks.
So thank you for very extensive talk. So we can take one or two quick questions.
Yes. Yes.
This point you are making about reheating just through gravitational coupling is very interesting.
Yes.
Now you produce so I guess in the diagram you have this graviton going into two gravitons. That's how you produce gravitational waves.
This one.
Yeah. So a graviton can go into two other gravitons.
Yes, you can have this process. You are talking about this. Yes.
So now my question is that this bound you are getting from BBN.
Yes.
Okay. This should be true for all models. Why are you restricting to this alpha models? Because this is at the stage of reheating.
No. In this particular context.
Yeah, but this should be true in general, right?
Yes.
For any inflation model, you should have some.
Yes. As long as
this diagram should exist.
No. One point I should emphasize here that it is not true for any model. One thing that is very important here is the equation of state. So during reheating, if your equation of state is less than 1/3, then this such bound does not arise. So typically what happens, if you look at the spectrum, if your equation, so basically this spectrum, this slope is very much dependent on, if you look at, I think I have this session. Yes. So if you look at this omega GW spectrum, it depends on this, it has an index, and index depends on what is the equation of state during the heat. And what happens here, if your equation of state is greater than 1/3, then only you have this positive slope, and there is a possibility that this slope can hit this BBN line. But if your equation of state is less than 1/3, this will go down. So there is no such bound coming from BBN.
And this equation of state depends upon what?
This equation of state is essentially inflaton parameter.
No, the mass of the inflaton during.
No, it is n, the power of the inflation.
So for instance, for the Goldstone boson, what would be the?
No, if you have simply phi square potential, like let's say axial inflation, this bound will not there.
Okay, okay.
So any other quick question?
Yeah. Phi 4, it is just constant line. Phi 4 is this one. Yes, 130. Yes.
In your analysis, the mass of the dark matter for each alpha value is heavily constrained, right?
Yes.
So going to the last cross section versus mass graph.
Yes.
Yeah, it seems that for a single mass, there can be two cross section values for some mass ranges. So does it?
Something like this you are saying?
Yeah.
Okay, so that is why I said ignore this. So this point is the point. So basically what happens is that what is happening here, this line is essentially radiation domination. Now if you go, this going down means actually your freeze out is happening inside the radiation. And then in order to get the correct relic, your coupling has to be small such that your cross section has to be small. And then gradually you reduce further down. Then moment you go after this freeze out mechanism will not occur. So below this point is essentially freeze in mechanism. Sorry, extremely sorry. Yes, sorry. Yeah, so that is why you have, so sorry. Yeah, you can here, I think this plot is, so basically this line is a freeze in, and this from point this onward you have freeze out. This is a freeze out and this is freeze in. So that's why for a given value of mass, you can have two mechanisms by which you can get the relief. One is for freeze in, if the coupling is very small. Another is freeze out when your dark matter is in thermal bath.
Okay.
Those are the 2 points. Yes.
Okay, and another question is, like constraining the mass to that narrow region,
Yes.
won't it have astrophysical implications? Like,
yes, so that is the point that, so basically here when I'm saying constraining, as I told you, as I repeatedly telling you, so when I'm talking about this mass range, I have taken that there is no coupling of the dark matter with any standard model, anything. Just there is a massive dark matter field and it is producing gravitationally because of during this heating. That's all.
that's fine. But what I'm trying to say is, wouldn't the size of dark matter halos, for example, when they are formed, they would be very uniform, which is not observed. Like if there's only a certain mass dark matter present, then following gravitational collapse, the nature of dark matter halos, won't that be too uniform, like which is not observed?
I think I have not understood your question properly. So basically, when I'm saying within this range, what it is, if you look at this alpha equal to 1, when this talking about this range, this depending on alpha. Sorry, this depending on equation of state. So for if you're talking about a very specific inflation model, then all this dark matter mass should be a unique value, and that dark matter mass is the prediction of this kind of scenario.
Yes, and
Now,
yes. Then that would mean that the astrophysical significances would also be dependent upon this mass. And
yes, that is true, that we have not performed that analysis, but yeah, what would be the astrophysical consequences of this? We have not performed this analysis. I think it is interesting to talk about those. You're talking about other observable aspects which can also further constrain. Yes, that is possible. So maybe that within this range, there is only one particular value will satisfy. Then you can see, that is what I'm saying. So if you say that within this range, one particular mass value is satisfied, that means it actually picks which inflation model to choose.
Yes, that's correct. Okay, maybe we can talk about it.
Maybe we can take more questions during discussion session, and let's move to the second talks. Thank you.